In this video, we will do a common and simple allowable stress design beam design. In this particular case, we are given some information, and you can see a picture here depicting the beam that we are going to design. We have a simply supported beam. It's 10 feet long, and it has a uniformly distributed load on it. We are also going to be bending this beam about the strong axis in bending. That is the XX axis. We can see the cross section of the beam right here on the right hand side at the right end of the picture of the beam here. If we look carefully at the given information, we see that the loading is due to a distributed dead load of 100 pounds per lineal foot. We also see a distributed load of roof live load of 120 pounds per lineal foot. We are also given in this problem that we are going to use Douglas fir number 1 type wood. So that is a Douglas fir species, and the grade of wood is number 1. We also have been provided with a specification for the deflection criteria. It is often given as a ratio of span length in inches divided by some number. In this case, a popular one or a common one that is required by building codes is L/240 when considering deflections due to dead load plus roof live load. We also state here that in this particular case, we are assuming that this beam is not a repetitive member. In other words, there are not multiple beams like this that are spaced at 2 feet or less, and so we don't get to use the repetitive use member in this particular problem. We also stipulate that continuous lateral support of the compression edge for this beam is provided. And so we will not have to worry about using the beam stability factor C sub L. In fact, C sub L for this case would just be 1.0. This is going to be very common for a roof or a floor system, since the plywood on the roof or the plywood on a floor would be nailed into the top portion of this beam, which is the compression edge. Hence, that compression edge is not allowed to move laterally because the plywood would not allow it to move side to side and try to buckle. Hence, continuous lateral support is assumed to be provided in this problem. In this case, we are also simply given a beam size, and we are going to check and see if this beam size is adequate for the loads and the deflection criteria that are prescribed in this problem. This is a 4x10 beam that we are assuming that we're going to check out. We also have listed here the section properties for this 4x10 beam. These properties are calculated based on the actual dimensions of the beam. And so of course we have the area here, 32.38 inches squared. We have the section modulus about the x-axis, 49.91 inches cubed. And we also have the moment of inertia about the x-axis, 230.8 inches to the fourth. In this problem, the required task that we are supposed to solve is basically this question: is the beam adequate for shear, bending, and deflection based on this given information provided above? So the solution would proceed as follows. First off, we notice that we have a load combination of dead plus roof live. In this case, you're not given any other loads, so all you can assume is that dead load and roof live load are provided. And so this is the only load combination we will consider because we don't have any other information. In other problems, you may be given multiple different types of loads, and hence you would have to consider perhaps more load combinations to see which ones might govern. But in this case, we're considering the load combination that contains dead plus roof live. If we do that, then we see that the distributed dead and the distributed roof live add up to give us 220 pounds per lineal foot. For a simply supported beam with uniform load, we need to check the shear capacity of that beam. And we need to do that according to the prescribed procedure provided by ASD. And so we start with this basic equation here. FV prime, the allowable stress, needs to be greater than or equal to the actual stress. With this equation as our guide, we can first check shear and see whether or not the beam is adequate for shear. In order to do that, we first need to find the maximum shear in the cross section of the beam. In this case, for a simply supported beam, we have that Vmax is going to be equal to WL over 2. And so if we calculate that, 220 times 10 over 2 is 1,100 pounds. From that, we can calculate the actual stress, F sub V, and it is equal to 1.5 times Vmax over A. That is a formula that we would find for a rectangular cross-section of a beam, and that comes from our shear stress formulas from basic mechanics of materials. If we plug in the values here, 1,100 pounds for Vmax and also the cross-sectional area of the beam, we can calculate from this that the actual shear stress is 51 psi. The allowable stress in shear will be FV prime, and so we must look up this table value, and we can do that by looking at the NDS supplement. And here you can see that for Douglas fir, Doug fir number 1, and for shear stress, we can see that right here the shear stress from the table is 180 psi. Going back to our example, we see here we have 180 psi for F sub V, and we also have the duration factor, C sub D. It is 1.25 for roof live load. If we were to go and look in the NDS and see if there were any other applicable factors, adjustment factors, we would see that based on the information given in this problem, we're assuming that the temperature is not excessively high, and also that the wood does not have a moisture content above 19%. Hence, those things will not affect this problem. Oftentimes, moisture and temperature are never an issue for us to be concerned with. For shear stress design, this is usually what you're going to see. So 180 times 1.25 is 225 psi. Clearly, that number, the allowable shear stress, is greater than 51 psi, and hence we can say that FV prime is greater than FV. That means the beam for shear is adequate. We can now move on to bending stress. So here is the bending check. We want now our allowable stress equation to be satisfied. That is that FB prime we want to be greater than or equal to FB in order for us to have a safe design. The first thing we need to do is find the maximum moment along the beam that we are designing. And because this is a simply supported beam, we know from basic statics that the maximum moment will occur at mid-span, and it will be WL squared over 8. This is, of course, for a simply supported beam with a uniform load on it. If we had a different loading or we had different supports, then this would not be applicable to our situation. But since it is uniform load, simply supported beam, this is going to work for us to find the maximum moment. And so we have 220 pounds per lineal foot times the span squared, which is 10 squared, all divided by 8, and we get 2750 pound-feet for our units of moment. The actual stress, F sub B, then can be calculated as M max divided by the section modulus about the x-axis. That is equal to 2750 times 12, so that we can convert this moment into pound inches. Because we are dividing by inches cubed, we need to have consistent length units, and hence that's why you're seeing this conversion factor on top of this equation. So we get that calculation accomplished, and we get 661 psi for the actual bending stress. The allowable bending stress is FB prime, and it is equal to FB times CD times CF. Again, if you look in the NDS in the table for adjustment factors that would be applicable to bending, you would find by looking at that list that these are really the only ones that apply to our situation. So we also need, of course, here to look at FB, and let's go back to our supplement table, and we can see for Douglas fir number 1, for bending FB, we have a value of 1000 psi. Going back now to our example, you can see that that is what we have put into our equation. We have 1.25 for C sub D. We also have 1.2 for C sub F, which is the size factor. Let's take a look at the supplement and see how it is that we got that C sub F factor. If we look right here and take a look down at this table at the bottom of this page, we can blow that up and look down at the C sub F factor for a 4x10. And we see here that we have, for a grade of number 1, we have a 4x10, so it's 10 inch in depth. And so 4x10, and we are doing bending. And so our C sub F factor is this 1.2 value right here from the table. Going back now again to our example, we see the C sub F factor is 1.2. Doing this calculation, we get an FB prime value of 1500 psi. Clearly, that number is greater than the actual stress. So our allowable stress is greater than the actual stress caused by the applied loads. And that then ensures a safe condition. We have not exceeded this allowable stress. So we can conclude that our beam is adequate for bending. The last thing we need to do that is common according to the code is we need to check deflections. We do not want beam deflections to be too excessive, and hence it is common for a deflection limit to be prescribed. Now in this expression, I'm trying to make it look like an allowable stress design equation. You may not see other people write it this way, but I'm trying to have a capital delta with a prime on it to indicate that this is kind of in the same form as allowable stress design, where this left-hand side is the value that is allowed and the right-hand side is the value that is actually being caused by the applied forces. So first, we'll calculate the actual deflection. For a uniformly loaded, simply supported beam, the deflection at mid-span, which is the biggest deflection location, we have 5WL to the fourth over 384 E prime times I, and that will be IX. We have then to put in the values, so we have 5, 220 pounds per lineal foot. And you'll notice that we have a 12 here on the bottom of the equation, and that is because this 220 pounds per lineal foot needs to be converted to pounds per inch. So this 12 on the bottom is actually converting this 220 to pounds per inch. The 384 is just a constant from the original formula. We also have our 10-foot span times 12, again, to convert that to inches. And hence, everything is in pounds and inches now. We also have our modulus of elasticity, and we find that there are no adjustment factors in this case for the modulus of elasticity. And that 1.7 times 10 to the 6 value we get from the supplement. Let's take a look at where we got that value. And again, if we go to Douglas Fir and we look at number 1 grade and we go all the way across, we can see that this value here, 1.7 times 10 to the 6 psi, is our E value. We do not use the E minimum value in this particular case. E minimum is only used if we were going to look at some stability problems. And in this case, we are not. And in fact, whenever you're doing deflection, you're going to use E. E minimum is only going to be used to calculate C sub L or C sub P. And we do not need to do that in this problem. So going back to our formula here, we see that we have E of 1.7 times 10 to the 6, no adjustment factors, and hence E is equal to E prime. We also have the modulus, or I should say the moment of inertia is what I mean to say, Ix, and so that's 230.8 inches to the fourth. This calculation yields an answer of 0.126 inches. Now we calculate the allowable deflection, capital delta prime. And so we have L over 240 as our deflection limit. So we take the span, which is 10 feet, times 12 to get that into inches, and divide by 240. And so we get an allowable deflection of 0.5 inches for this particular beam. Clearly, 0.5 is greater than 0.126. So delta prime is greater than little delta. So we can conclude that our beam is adequate for deflection. Now, if you recall each of these things that we've checked, which is shear, bending, and deflection, you will see that in all cases, our allowable value was quite a bit bigger than the actual values of stress or deflection that were being caused. And hence, looking back at the results, a smaller beam is warranted. It would certainly be okay for us to use a 4x10, but it's very likely that either a 4x6 or a 4x8 would work. And so that would be a very good exercise for someone to go back through this very same process and see whether or not one of these smaller beams would work. That would be saving some weight of the beam and also allow you to have a beam that maybe would cost a little bit less. Now, one other thing that occurs to me to comment on is that we were given the dead load at the very beginning of this problem, and that assumes that the weight of the beam itself was already included in that dead load. And of course, that is what I was assuming when I did this example. Anyway, this is a very good example for seeing the basics of allowable stress design as applied to beam design. Now, there are other ways to do it, but we have done it here starting from the very fundamental equations of allowable stress design. In some future videos, we may illustrate some other ways of doing beam design, particularly for these simple cases where we have a uniform load and a simply supported beam Since that is so very common, it would be nice to have a streamlined method for doing that. For more challenging problems, sometimes what we have illustrated here is really the way to go. So don't ever lose sight of the fact that using the allowable stress design equations is always applicable. Thank you for watching this video, and I hope that is helpful to you.